In the world of industrial automation and controls engineering, there's a super important concept called PID loops, or proportional integral derivative. And they're calculations that are done for analog process control of things like pressure, temperature, or flow, typically using an analog control component like the speed a motor turns at or the percent open of an analog control valve, to try to drive that process value to a certain set point. The task of tuning these is critically important, and understanding what they are and how they work is also super important. P, or proportional, is the easiest one to understand. In the setting of like cruise control on your car, which is probably the most common, frequently interacted with consumer PID loop, if you tell your car that you want it to maintain 65 miles an hour, the proportional is how aggressively it will attempt to correct error based on how far off from the set point it is. So obviously, if you're cruising at 55 miles an hour, but your target set point is 65 miles an hour, give the car a little more gas than it would if you were at 64 miles an hour. And the higher you make your P value on your PID loop, more aggressively the car will attempt to correct for that error. But integral, or the I, is where it starts calculating how long has it been above or below the target set point. And this computation will sort of put its finger on the scale. So if you've been creeping towards your set point for a very long period of time, a higher I value will say, hey, that's unacceptable. It's taking too long to get to your set point, and it'll start accelerating the speed at which you pursue that set point a little more aggressively. And D, which stands for derivative, is definitely the most finicky aspect of a PID loop. Derivative is a predictive element which sees the rate at which you're approaching your set point and the rate of change you've been experiencing, and it will try to predict what's going to happen in the system next and start preemptively tapering off as you get closer to the set point. Tuning PID loops is one of the core jobs of a lot of controls and automation engineers. And how do you go about it? There's a math-based, science-based, data-based way called the Ziegler-Nichols method, where you sort of run a data and math-based trial to calculate key parameters and starting points for your tuning, and then you tweak those parameters based on real world after you find that starting point. However, I've worked with a lot of great automation engineers who are not running those analyses, and they just have like their lucky socks version of PID parameters that they start with, and you can sort of just observe the system from there. There's also many PLC manufacturers that will let you plug your PID set point, process value, and control value into PID loop tuning software, and it'll spit out what it calculates to be ideal parameters. You're not completely going in alone, but you need to understand what these are to properly understand how to work with them and how to tune them.